Imagine you are a detective. You know someone has committed a crime. You are absolutely certain of it. The evidence is everywhere. Fingerprints that do not match anyone in the database. Money that vanished into thin air. Witnesses who saw something impossible happen. But here's the problem. You cannot find the criminal. You have searched everywhere. You have used every tool at your disposal. And still, nothing. What do? You look for what the criminal left behind, not the criminal themselves, not even a photograph. You look for the tiny, almost invisible traces, the fiber caught on a doorframe, the faint footprint in the dust, the fingerprint on a glass that was not supposed to be there. And that is exactly what is happening right now, at this very moment, in laboratories scattered across the world. Physicists are not looking for new particles. They are looking for fingerprints, echoes, shadows cast by something they cannot see. Because there is a criminal hiding in the universe, something beyond our current understanding of physics. And the only way to catch it might be to watch particles do something they are not supposed to do. Let me take you back to 1947. In a basement laboratory at the University of Manchester, two physicists named George Rochester and Clifford Butler were staring at a photograph. They had been studying cosmic rays, high-energy particles that rain down from space, colliding with atoms in Earth's atmosphere and creating showers of secondary particles. To track these particles, they used something called a cloud chamber, a device filled with supersaturated vapor that revealed particle tracks like contrails behind an airplane. And in that photograph, they saw something strange. Two particles had appeared out of nowhere. Their tracks formed a shape like the letter V, forking outward from a single point. But here was the puzzle. The particles that made those tracks were familiar, ordinary. The mystery was what had created them. Something invisible, something that had traveled a short distance after being produced and then suddenly decayed into those two visible particles. Rochester and Butler had discovered a new particle. They did not know it yet, but they had just opened a door that would transform our understanding of the universe. They called them V particles at first because of the shape of their tracks. Later, scientists would give them a more evocative name, strange particles. The name was not chosen arbitrarily. These particles were genuinely strange. They were produced abundantly in cosmic ray collisions, which meant the force creating them was strong. But they decayed slowly, roughly a trillionth of a second, which sounds fast, but is actually 100 billion times slower than particles of similar mass typically decay. How could something be created quickly but decay slowly? It was like watching someone sprint up a mountain in seconds and then take hours to walk back down. The physics did not make sense. In 1953, a young physicist at the University of Chicago named Murray Gell-Mann proposed an answer. What if these particles possessed a new quantum property? Something that had to be conserved when they were created, but could be violated when they decayed. Gell-Mann called this property strangeness. Working independently in Japan, Kazuhiko Nishijima arrived at the same idea. Their insight was profound. Strange particles were always produced in pairs, with one particle having strangeness of +1 and another having strangeness of -1. The total strangeness was 0, satisfying the conservation law. But when these particles decayed through the weak nuclear force, strangeness was not conserved. The decay could change strangeness by 1 unit at a time, which explained why it took so many steps and therefore so much time. This was more than just an explanation for a puzzle. It was the first glimpse of a hidden structure beneath the zoo of particles that physicists were discovering. Gell-Mann would go on to organize particles into elegant patterns based on their strangeness and electric charge, a scheme he called the Eightfold Way, borrowing the name from Buddhist philosophy. And when he tried to explain why the patterns worked, he was led to a radical conclusion. All these particles were made of something even more fundamental. In 1964, Gell-Mann proposed that hadrons, the particles that feel the strong force, were built from smaller constituents. He called them quarks, borrowing the word from a line in James Joyce's Finnegan's Wake. 3 quarks for muster mark. The strange particles, including the kaon that Rochester and Butler had discovered, were strange because they contained a strange quark, a type of quark that had never existed in ordinary matter. Now, why am I telling you about particles discovered nearly 80 years ago? Because those strange particles, especially the kaon, turned out to be one of the most powerful tools in physics. Not for what they are, but for what they do. More specifically, for what they do when they decay. Here is the key insight. When particles decay, they do not simply fall apart. The decay happens through an intermediate process involving quantum fluctuations, a term that sounds mystical but actually refers to something very precise. In quantum mechanics, particles can briefly borrow energy from the vacuum and create virtual particles that exist for only an infinitesimal moment before vanishing. These virtual particles are not real in the sense that you could detect them directly. They are more like accounting entries in nature's ledger, temporary deviations that must balance out. But here is the thing. Those virtual particles can be anything. When a kaon decays, it does not just transform directly into its final products. The decay proceeds through a loop diagram, a process where the kaon's quarks emit and absorb virtual particles, including extremely heavy particles like W bosons and even top quarks, which are more than 300 times heavier than the kaon itself. How can a particle that weighs less than a gram create something that weighs 300 grams, even briefly? Because it does not really create it in the normal sense. The virtual particle exists in a kind of quantum superposition, a mathematical possibility rather than a physical reality. And yet, those virtual particles influence the probability of the decay occurring. This is where it gets interesting. If new particles exist, particles we have never detected, particles that might be too heavy for even our most powerful colliders to produce, they could still appear in those loop diagrams. They would be virtual, borrowing energy from the vacuum, just like the known particles. And they would change the decay rate. The decay would happen slightly more often or slightly less often than the standard model predicts, depending on whether the new particle's contribution adds to or subtracts from the existing amplitudes. This is the fingerprint. This is the trace left by a criminal we cannot catch directly. The Large Hadron Collider is the most powerful particle accelerator ever built. It sits beneath the Franco-Swiss border, a ring of superconducting magnets stretching 27 kilometers in circumference, accelerating protons to 99.99999% of the speed of light before smashing them together with energies of 13.6 trillion electron volts. When those protons collide, the energy can transform into matter according to Einstein's famous equation. And for a brief moment, particles that have not existed since the first fraction of a second after the Big Bang can flicker back into existence. This is how we found the Higgs boson in 2012, the last piece of the Standard Model, the particle that explains why other particles have mass. But here is the limitation that few people talk about. The Large Hadron Collider has a resolution limit. It can directly probe distances down to about 50 zeptometers, that is 50 times 10 to the minus 21 meters, or 500 billionths of a trillionth of a meter. To put this in perspective, a proton is about a femtometer across, which is 10 to the minus 15 meters. The LHC can see things about 100,000 times smaller than a proton. That sounds impressive, and it is. But there is a whole universe of distance scales smaller than what the LHC can reach. The LHC can directly discover new particles up to a few tera-electron volts in mass, roughly a few thousand times heavier than a proton. Beyond that, the particles are simply too heavy to produce, even in the highest energy collisions. And this is the frustration that has haunted particle physics for more than a decade. Since the Higgs discovery, the LHC has searched tirelessly for signs of new physics, supersymmetric particles, extra dimensions, dark matter candidates, and found nothing. Every search has come back empty. The Standard Model, which we know cannot be the complete picture, continues to work perfectly within the LHC's energy range. The new physics we are seeking must be hiding at higher energies, but we cannot build a collider powerful enough to reach those energies. Not yet, not for decades, maybe not for the rest of this century, unless we find another way. This brings me to André Bourras. Bourras is a theoretical physicist at the Technical University of Munich, and he has spent decades thinking about this problem. He is not trying to build a bigger collider. He is trying to find a back door. In a series of papers stretching back to 2014, Bourras laid out a strategy for what he calls reaching the Zeptouniverse, the realm of physics at scales of 10 to the minus 21 meters, corresponding to energies around 200 tera-electron volts. That is roughly 10 times smaller and 10 times more energetic than anything the Large Hadron Collider can directly probe. How can you possibly study distances you cannot reach? The answer lies in rare decays. Bourras's insight builds on a simple fact. When particles decay through loop diagrams, the virtual particles in those loops can have any mass. A kaon decay can involve a virtual top quark, even though the kaon is hundreds of times lighter than the top quark. But more than that, if a new particle exists at 200 tera-electron volts, it can also appear in those loops. The key is that different masses contribute differently to the decay amplitude. Heavy virtual particles are suppressed by factors involving their mass. The heavier they are, the smaller their contribution, but they still contribute. And here is the crucial point. Certain rare decays are so precisely predicted by the Standard Model and so sensitive to new physics contributions that even a tiny discrepancy would be detectable. The Standard Model predicts that certain kaon decays should happen fewer than once in 10 billion events. If the measured rate is even slightly different, say 13 in 10 billion instead of 8 in 10 billion. It could be definitive evidence of new physics at energy scales we cannot directly reach. Burrus identified 7 specific decays that he believes represent the best targets for this indirect search. He calls them the Magnificent Seven. Let me tell you about each of these decays and why they matter. The first is the charged kaon decay into a pion and 2 neutrinos. Written in physics notation, this is K plus going to pi plus nu bar. It happens when a positively charged kaon, which contains an up quark and a strange antiquark, transforms into a positively charged pion, which contains an up quark and a down antiquark, along with a neutrino-antineutrino pair. At the quark level, this requires the strange antiquark to change into a down antiquark while emitting a neutrino, an antineutrino. This is what physicists call a flavor-changing neutral current process. Now, here is what makes this decay so special. In the standard model, flavor-changing neutral currents are extremely suppressed. There is no way for a quark to change flavor by emitting a neutral particle, like a photon or a Z boson at tree level, meaning in the simplest, most direct diagram, the process can only happen through loops. This suppression has a name, the Jim mechanism, named after Sheldon Glashow, John Iliopoulos, and Luciano Maiani, who discovered it in 1970. The Jim mechanism is beautiful in its simplicity. When you calculate the loop diagram for a kaon decay, the contributions from different virtual quarks interfere with each other. The up quark contribution partially cancels the charm quark contribution, and both are modified by the top quark contribution. If all the quarks had the same mass, the cancellation would be perfect and the decay would never happen. But the quarks do not have the same mass. The top quark is vastly heavier than the charm and up quarks. This imperfect cancellation leaves a tiny residual amplitude that makes the decay possible, but extremely rare. The standard model predicts that roughly 8 kaons out of every 10 billion will decay this way. The uncertainty on this prediction is only about 5%, one of the most precise predictions in all of flavor physics. And this precision is exactly what makes the decay valuable. If new particles exist at high energies, they can enter the loop diagram and modify the decay rate. Depending on the nature of the new physics, the rate could increase or decrease. Either way, a discrepancy with the standard model prediction would be unmistakable. The experiment hunting for this decay is called Na-62, and it runs at CERN. Na-62 produces kaons by slamming a beam of 400 billion electron-volt protons from CERN's superproton synchrotron into a stationary beryllium target. The collisions create a shower of secondary particles, roughly 1 billion per second, streaming into the detector. About 6% of these particles are positively charged kaons. The detector then tracks each kaon as it flies through, watching for the moment of decay. The challenge is extraordinary. The decay you are looking for happens fewer than once in 10 billion times, and the signal, a single pion plus missing energy from the invisible neutrinos, can be mimicked by numerous background processes that happen vastly more often. The most common kaon decay, for instance, is into a muon and a neutrino. This happens about 64% of the time. If the muon is misidentified as a pion, it looks exactly like the signal you are seeking. To suppress these backgrounds, Na-62 uses a suite of sophisticated detectors. Tracking chambers measure particle trajectories with micrometer precision. ring imaging Cherenkov detectors identify particle types by the patterns of light they emit. Electromagnetic and hadronic calorimeters measure particle energies. Veto detectors catch any extra particles that might indicate a background event. For more than a decade, the collaboration painstakingly collected data and refined their analysis techniques. They developed new methods to reject backgrounds. They upgraded their detectors to handle higher beam intensities. And in September of 2024, they announced a breakthrough. At a seminar at CERN on September 24th, Na62 reported the first observation of this ultra-rare decay at discovery-level significance, 5 standard deviations, the gold standard in particle physics. They had collected enough events to measure the branching ratio, about 13 kaons in every 10 billion decay this way. That number is roughly 50% higher than the standard model prediction of about 8 in 10 billion. Now, I need to be careful here. The measurement has a significant uncertainty, about 25% relative precision. When you account for the uncertainties on both the measurement and the prediction, the numbers are statistically compatible. There is no definitive disagreement yet, but the hint is tantalizing. Giuseppe Ruggiero, the Na62 spokesperson, described it as the culmination of a project that started more than a decade ago. He added that looking for effects in nature that have probabilities of happening of the order of 10 to the minus 11 is both fascinating and challenging. The experiment continues to collect data. Within the next few years, they hope to either confirm or rule out the presence of new physics in this decay. The second member of the Magnificent Seven is the neutral version of the same decay, a long-lived neutral kaon decaying into a neutral pion and 2 neutrinos. This decay is even more interesting than its charged counterpart because it directly violates a symmetry called CP. CP stands for charge parity. The C operation replaces every particle with its antiparticle. The P operation reflects the universe in a mirror, flipping left and right. If physics is CP symmetric, then a process and its mirror image antiparticle version should behave identically. For most of physics, CP symmetry holds perfectly, but in certain weak interactions, especially those involving quarks changing flavor, CP is violated. CP violation was first discovered in kaon decays in 1964, a discovery so important that it earned the Nobel Prize for James Cronin and Val Fitch in 1980. And CP violation is not just a curiosity. It is one of the 3 necessary ingredients identified by Andrei Sakharov for explaining why the universe contains more matter than antimatter. The neutral kaon decay into a pion and neutrinos is a direct probe of CP violation in the quark sector. The standard model predicts this decay should happen about 3 times in every 100 billion kaons, roughly 3 times rarer than the charged version. The experiment searching for this decay is called KOTO, and it operates at the Japan Proton Accelerator Research Complex, known as JPARC. KOTO faces an even greater challenge than Na62. The final state consists entirely of neutral particles, a neutral pion, which decays almost instantly into 2 photons plus neutrinos that cannot be detected at all. The signal is literally 2 photons plus nothing. To identify this, KOTO uses a massive electromagnetic calorimeter made of cesium iodide crystals to detect the photons. Surrounding the decay region are hermetic veto detectors that catch any additional particles that might sneak through. In 2018, Koto set the world's best upper limit on this decay. Fewer than 3 in a billion kaons decay this way. That is still about 100 times higher than the standard model prediction. So there is room for the experiment to improve before they can test the theory. The search continues. The third and fourth members of the Magnificent Seven involve a different particle, the B meson. B mesons contain a bottom quark, also called a beauty quark, one of the heaviest quarks, with a mass about 4 times that of a proton. When paired with an up or down antiquark, you get charge and neutral B mesons. Like kaons, B mesons decay through weak interactions, and their decays can probe physics at very high energy scales. The decays Buras highlighted are B plus going to K plus a nu bar, a B meson transforming into a kaon and 2 neutrinos, and the related decay involving K star, an excited state of the kaon. These decays are conceptually similar to the kaon decays I described earlier. A bottom quark changes into a strange quark while emitting a neutrino-antineutrino pair. The process is suppressed by the JIM mechanism, making it extremely rare, and it is sensitive to new physics contributions. The standard model predicts branching ratios around 5 in a million for these decays. Rare, but not as crushingly rare as the kaon decays. The experiment hunting for these decays is Belle de CERN, located at the Super Kegbe Collider in Tsukuba, Japan. Belle 2 takes a completely different approach than NA62 or Koto. Instead of using a fixed target, it collides electrons and positrons, tuning the energy to produce pairs of B mesons from the decay of a resonance called the upsilon 4s. The beauty of this technique is that B mesons are produced in pairs. If you can fully reconstruct one B meson, measuring all its decay products, you know exactly what the other B meson must be. This allows you to deduce the presence of invisible particles like neutrinos from the missing energy. In August 2023, Belle II announced the first evidence for the B plus to K plus nu bar decay. Their measurement showed a signal at 3.5 standard deviations, not quite the 5 sigma threshold for discovery, but strong evidence that the decay exists. And intriguingly, their measured rate was about 2.7 sigma, higher than the standard model prediction. Again, we must be cautious. The uncertainties are still large. But combined with the NA62 result, a pattern may be emerging. Both kaon and B meson decays to neutrinos are appearing at rates slightly higher than expected. If this pattern holds as more data accumulates, it could be pointing to new physics that enhances these particular processes, perhaps a new heavy particle that interferes constructively with the standard model amplitude. The fifth and sixth members of the Magnificent Seven are B meson decays to muon pairs. Specifically, Buras highlighted B sub s going to mu plus mu minus, a strange B meson decaying into a muon anti-muon pair, and the similar decay of the ordinary B sub d meson. These decays have a different character than the neutrino modes. Instead of missing energy, you get 2 charged particles that can be precisely tracked and measured. The standard model predictions are exquisitely precise. The B sub s decay should happen about 3 times in a billion, with uncertainties at the few percent level. The B sub d decay is even rarer, suppressed by an additional factor from the CKM matrix, the table of numbers that describes how strongly quarks couple to each other through the weak force. These decays were first observed in 2014 through a combined analysis by the CMS and LHCb experiments at the Large Hadron Collider. It was a triumph of precision measurement, confirming a prediction that had been sought for decades. And the measured rate? Right on top of the standard model prediction. Unlike the neutrino modes, these decays show no hint of deviation. At least not yet. But that is actually valuable information. The agreement tells us that certain types of new physics, specifically new particles that would contribute to these decays at tree level rather than through loops, must be either very heavy or very weakly coupled. It constrains the possibilities. The seventh member of the Magnificent Seven is a bit different. It is not a single decay, but a property of the decay. The lifetime of the B sub S meson in its decay to muon pairs. When you measure a decay, you measure not only how often it happens, but how the decay products are distributed in time. The B sub S meson is a quantum superposition of a particle and its antiparticle, and this mixing leads to subtle effects in the time distribution of decays. The standard model makes precise predictions for these time-dependent observables. Deviations could signal new sources of CP violation. The asymmetry between matter and antimatter that we desperately need to understand. So far, the measurements agree with predictions, but the precision is still limited, and this remains an active area of research. Now let me explain why these particular 7 decays are so powerful. It comes down to a concept that physicists call theoretical cleanness. Not all rare decays are created equal. Some decays involve complicated strong interaction effects that are difficult to calculate. The quarks inside a meson are bound together by the strong force, and disentangling the weak interaction physics from the strong interaction physics can introduce large uncertainties. But the Magnificent Seven are special. They involve processes that can be calculated with remarkably small theoretical uncertainties. The kaon decays to pion plus neutrinos, for instance, are dominated by short-distance physics, interactions happening at scales much smaller than the size of the kaon. At these scales, the strong force is relatively weak and perturbative calculations work well. The main uncertainty comes not from quantum chromodynamics, but from our knowledge of the CKM matrix elements, the fundamental parameters that describe quark mixing. And Burris developed clever techniques to eliminate this uncertainty by comparing the rare decays to other well-measured quantities, like the mass differences in B meson mixing. The result is that these decays can be predicted to 5 or 10% precision. Good enough that deviations at the level of 50% would be clearly visible. Compare this to other flavor physics observables, where theoretical uncertainties can be 30 or 50%. In those cases, even a large new physics contribution would be hidden in the noise. The Magnificent Seven are the precision instruments of flavor physics. They are the places where a discrepancy means something. So what kind of new physics could explain the tentative hints we are seeing? Let me describe 2 candidates that theorists have proposed. The first is a Z-prime boson. In the standard model, there is one neutral gauge boson that mediates weak interactions, the Z boson, with a mass of about 91 billion electron volts. But many extensions of the standard model predict additional Z-like bosons called Z-prime particles. These Z-prime bosons would have their own couplings to quarks and leptons. Depending on those couplings, They could enhance or suppress various rare decays. If a Z-prime boson exists with a mass in the range of tens or hundreds of tera-electron volts, it would be far too heavy to produce at the LHC, but it could still appear as a virtual particle in the loop diagrams for kaon and B Mason decays. The pattern of enhancements and suppressions across different decay modes would depend on the Z-prime's couplings, providing a way to diagnose its properties even without producing it directly. The second candidate is a leptoquark. Leptoquarks are hypothetical particles that carry both quark and lepton quantum numbers. They would mediate interactions that directly connect quarks and leptons, something that does not happen in the standard model, except through the weak force. Leptoquarks are motivated by grand unified theories, which attempt to unify the strong and electroweak forces into a single framework. They are also invoked to explain certain anomalies in B meson decays that have appeared over the past decade. If leptoquarks exist with masses in the tera-electron volt range, they could contribute to the rare decays we have been discussing. Their contributions would be different from Z-prime contributions, potentially distinguishable through the correlations between different decay modes. This is the power of studying multiple rare decays simultaneously. Different new physics scenarios predict different patterns. By measuring all 7 of the Magnificent Seven, physicists can narrow down the possibilities. There is a mathematical relationship that governs the 2 kaon decays. In 1997, physicists Yuval Grossman and Joseph Neer proved that the neutral kaon decay rate must be less than 4.3 times the charged kaon decay rate, regardless of what new physics exists. This is called the Grossman-Neer bound, and it holds in essentially any model that respects basic principles like unitarity of the quantum mechanical S matrix. The bound arises because the charged and neutral kaon decays are related by isospin symmetry, a symmetry that connects processes involving up and down quarks. Even if new physics modifies both decays, it cannot violate this fundamental relationship. Right now, the charged kaon decay has been measured at about 13 in 10 billion. The Grossman-Neer bound therefore says the neutral kaon decay must be less than about 56 in 10 billion. The standard model predicts only 3 in 10 billion for the neutral decay. That leaves a huge window from 3 to 56 in 10 billion where new physics could be hiding. The Koto experiment is probing that window right now. If Koto finds a rate significantly above the standard model prediction, it would be revolutionary. It would mean new physics is present in the kaon system, contributing to CP violation beyond what the standard model allows. Let me step back and explain why all of this matters for the deepest questions in physics. The standard model is astonishingly successful. It has survived 50 years of experimental tests. Every particle it predicts has been found. Every calculation it enables has agreed with measurement, often to 10 or more significant figures. But we know the standard model cannot be the final answer. It does not include gravity. It does not explain why there is more matter than antimatter in the universe. It does not account for dark matter, which makes up about 27% of the universe's mass energy. It does not explain why the Higgs boson is so much lighter than one might expect from quantum corrections. These are not minor puzzles. They are fundamental gaps in our understanding, and the search for new particles supersymmetric partners, extra dimensions, dark matter candidates, were supposed to fill those gaps. The Large Hadron Collider was built to find them, but so far, nothing. The new physics must exist. The questions demand answers, but the particles that would provide those answers may be too heavy for the LHC to produce. This is why the rare decay strategy is so important. If new particles exist at energy scales of tens or hundreds of tera-electron volts, we cannot produce them directly with any accelerator that could be built in this century. The future circular collider that CERN is planning might reach 100 tera-electron volts, but it will not begin operations until the 2070s at the earliest. But we might not have to wait that long. The rare decays provide a window into those energy scales now, today, with experiments that are already running. André Bourras put it eloquently in a paper he wrote for CERN Courier. The search for new particles and forces beyond those of the standard model is strongly motivated by the need to explain dark matter, the huge range of particle masses from the tiny neutrino to the massive top quark, and the asymmetry between matter and antimatter that is responsible for our very existence, as direct searches at the LHC have not yet provided any clue as to what these new particles and forces might be. Indirect searches are growing in importance. There is a timeline here, and it is surprisingly short. NA62 is continuing to collect data. Their next analysis, incorporating data through 2025 or 2026, should reach the precision needed to definitively confirm or rule out the 50% enhancement they are seeing in charged kaon decays. Belle II is ramping up. The Super KEKB Collider is being upgraded to deliver higher and higher luminosities, more collisions per second, more B mesons, more data. They aim to accumulate 50 inverse attobars of data by the early 2030s, which would allow measurements of the neutrino decay modes at the few percent level. COTO continues its search for the neutral kaon decay. Upgrades to the experiment are planned that could push the sensitivity down toward the standard model prediction within this decade. And the LHCb experiment at CERN keeps improving its measurements of the B meson decays to muon pairs, constraining new physics from a complementary direction. Within 5 to 10 years, we could have definitive answers. If all the measurements converge on the standard model predictions, it will tell us that new physics, whatever it is, must be even heavier or more weakly coupled than we thought. The indirect searches will have set limits that no direct search could match. But if deviations persist and grow more significant, it will be a discovery as momentous as the Higgs boson, perhaps more so, because we would have found evidence for particles and forces beyond the standard model, entities that shape the universe at its most fundamental level, and we would have done it not by building a bigger collider, but by paying careful attention to the faint fingerprints left behind in the quantum vacuum. There is something philosophically profound about this approach to physics. We tend to think of discovery as dramatic, the moment when a new particle flashes into existence in a detector, its signature unmistakable. That is how the Higgs was found. That is how the top quark was found. That is the image of physics in the public imagination. But the universe does not always cooperate with our desire for drama. Sometimes the truth is subtle. Sometimes the evidence is statistical, emerging slowly from the accumulation of many small deviations. Sometimes you do not see the criminal. You see only the disturbed dust in the hallway, the faint scuff mark on the floor. The rare decay strategy embraces this subtlety. It requires patience, precision, and a willingness to accept that certainty comes gradually through the reduction of uncertainties and the comparison of multiple independent measurements. It is a different kind of physics, but it may be the physics we need. Let me tell you about the future. Assuming the hints persist and grow stronger, the natural next question is, what exactly is causing them? Different new physics scenarios predict different patterns of deviations across the Magnificent Seven. A Z prime boson would affect kaon and B meson, decays, in particular ways. A leptoquark would affect them differently. A model with right-handed currents would leave a distinct signature. By measuring all 7 decays precisely, physicists can construct what Burris calls a DNA chart, a unique fingerprint for each model. The combination of enhancements and suppressions across different channels would point toward a specific type of new physics. And once we know what kind of new physics we are dealing with, we can design experiments to study it further. Maybe the future circular collider with its 100 tera-electron volt collisions will be able to produce the new particles directly. Maybe a muon collider, which is currently being designed and could reach 10 tera-electron volts in a more compact facility, will be the right tool. Maybe entirely new technologies, plasma wake-field accelerators, for instance, will open up energy scales we cannot currently imagine. But none of that planning can happen until we know where to look. The rare decays are the scouts, the reconnaissance missions that tell us where the enemy is hiding. I want to end with a reflection on the nature of scientific progress. Physics has always been a dialogue between theory and experiment. The theorists propose, the experimentalists test. When the tests agree with the proposals, we gain confidence. When they disagree, we learn something new. For decades, the standard model has passed every test. It has been, in some sense, too successful. The agreement between theory and experiment has been so precise that it left no cracks for new physics to slip through. But cracks may be appearing. The excess in the charged kaon decay rate, the enhancement in the B meson to kaon neutrino mode. The hints, still tentative, still uncertain, but hints nonetheless. Maybe these will fade with more data. Maybe the central values will shift back toward the standard model predictions. That happens in physics. Statistical fluctuations can masquerade as discoveries. But maybe they will not fade. Maybe the hints will solidify into evidence, and the evidence into discovery. We are at a peculiar moment in the history of physics. The great triumph of the 20th century, the standard model, has been completed, and yet we know it is not the end. Dark matter exists. The matter-antimatter asymmetry exists. The hierarchy problem exists. Something beyond the standard model must be out there. We have been searching for that something for decades. We have built the largest machines in history to find it. And still, it eludes us. But it cannot hide forever. Every time a kaon decays in Geneva, every time a B meson decays in Tsukuba, the new physics leaves its mark. A tiny, almost imperceptible change in the probability. A fingerprint in the quantum vacuum. We are learning to read those fingerprints. We are building the tools to detect those marks. And when we finally catch the criminal, when we finally understand what lies beyond the standard model, it may not be through a dramatic collision in a giant accelerator. It may be through the patient accumulation of rare events, the statistical evidence building slowly over years, 7 decays, each predicted with extraordinary precision by the standard model, each sensitive to new physics at energy scales 10 times beyond what any current collider can reach. They are CERN's secret weapon, and they may be our best hope for breaking physics wide open. The search continues. In laboratories around the world, detectors are watching, recording, analyzing. Billions of kaons are produced every year, millions of B mesons. Each one a lottery ticket, a chance that this particular decay will be the rare one, the one that happens fewer than once in 10 billion tries. The physicists running these experiments are patient. They have to be. This is not the physics of instant gratification. This is the physics of the long game, the slow accumulation of evidence, the gradual reduction of uncertainty. But the stakes could not be higher. If new physics is found in these decays, it will reshape our understanding of the universe at its most fundamental level. It will open doors that have been closed for a generation. It will point the way toward answers to questions we have been asking since the beginning of science. What is matter made of? Why is there something rather than nothing? What are the ultimate laws that govern reality? And if the decays all agree with the standard model, even that would be profound. It would tell us that the new physics is hiding in places we have not thought to look, that our assumptions need to be revisited, that the universe is even stranger than we imagined. Either way, we learn. That is the beauty of science. Every result, whether expected or surprising, teaches us something. The universe speaks through data, and we are learning to listen. 7 decays, fewer than once in 10 billion, the fingerprints of the Zeptouniverse. Somewhere in those rare events, the answer is waiting, and we are getting closer, one decay at a time. I want to take you deeper into how these experiments actually work, because the engineering challenges are almost as remarkable as the physics. Consider what Na-62 is trying to accomplish. A beam of protons traveling at nearly the speed of light strikes a beryllium target. The collision produces a spray of particles, pions, kaons, protons, neutrons, traveling in roughly the same direction. This secondary beam is guided by magnets into a 240-meter-long vacuum vessel. Inside that vessel, each kaon is tracked as it flies forward. Most kaons travel about 700 meters before decaying, so the detector needs to watch each particle for the brief moments when decay might occur. The kaon enters the tracking region. Upstream detectors called the Geiger tracker measure its position and momentum with extraordinary precision, timing resolution of about 70 picoseconds, position resolution of about 100 micrometers. You need to know exactly where the kaon is and how fast it is moving, because you will need to calculate whether the decay products are consistent with the signal you seek. Then the kaon decays. If it is the rare decay, the 1 in 10 billion event, the kaon transforms into a pion and 2 neutrinos. The pion continues forward, but with less momentum than the original kaon. The neutrinos fly off invisibly, carrying away the missing energy. The downstream detectors catch the pion. A straw tracker measures its trajectory. Ring imaging Cherenkov detectors identify it as a pion rather than a muon. Because remember, kaons decay to muons. 64% of the time. And if you mistake a muon for a pion, you will be fooled. The Cherenkov effect is elegant. When a charged particle travels through a medium faster than light travels in that medium, it emits a cone of light, analogous to a sonic boom for sound. The opening angle of the cone depends on the particle's speed. Combine that with the measured momentum, and you can deduce the particle's mass. For a pion and a muon with the same momentum, the Cherenkov angles differ by about 2 degrees. That is enough to tell them apart if your detector is precise enough. Na62 uses 2 different Cherenkov detectors. One is filled with nitrogen gas, the other with neon. They provide redundant identification, reducing the chance of misidentification to negligible levels. But particle identification is not the only challenge. You also need to ensure that no other particles are present. Remember, the signal is a single pion plus missing energy. If a second particle escapes the detector, it can fake the missing energy signature. To catch these stowaways, Na62 surrounds the decay region with photon veto detectors. Any photon with energy above a few hundred mega-electron volts is detected with high efficiency. This rejects decays, where the Khan produces a pion and a neutral pion, which immediately decays to 2 photons, rather than a pion and neutrinos. Similarly, charge particle veto detectors catch any additional charged particles that might sneak through. The whole system achieves a background rejection of 10 orders of magnitude, a factor of 10 billion. That is necessary because the signal happens only once in 10 billion decays, and you need the background to be small enough that the signal stands out. Let me explain what happens when Na62 collects data. Over the course of a running year, the experiment records roughly 1 trillion kaon decays. That sounds like an enormous number, but it corresponds to only about 100 signal events if the standard model is correct. 100 events among 1 trillion. Finding them requires sifting through a haystack the size of a mountain to find a few hundred needles. The data cannot be stored raw. There is simply too much of it. Instead, the experiment uses a multi-level trigger system that makes split-second decisions about which events to keep. The first level trigger looks for simple patterns: the presence of a charged particle in the downstream detector, the absence of extra activity in the veto systems. It reduces the data rate by a factor of about 100. The second level trigger does more sophisticated analysis, reconstructing particle trajectories and calculating kinematic variables. It reduces the rate by another factor of 10. Only then is the data sent to permanent storage for later analysis. The offline analysis is where the real detective work happens. Physicists develop selection criteria, cuts in the jargon, that retain signal events while rejecting backgrounds. Each cut is carefully optimized. Too loose, and backgrounds overwhelm the signal. Too tight, and you lose signal efficiency. The final selection for the 2024 result required events in specific kinematic regions, identified by the squared mass of the missing system. The signal events cluster in 2 regions, separated by a window where background from ordinary decays dominates. When the collaboration unblinded their data, meaning they finally looked at the signal region after all the cuts were finalized, they found 51 events in one region and 115 events in the other. Combined with earlier data, this gave them enough statistics to claim observation. the Japanese experiments face their own unique challenges. Koto, searching for the neutral kaon decay, operates at J-Park's Hadron Experimental Facility. The neutral kaon beam is produced by firing protons onto a goal target, then selecting neutral kaons from the spray of particles using a carefully designed collimator. The challenge with neutral particles is that you cannot track them. A charged particle leaves ionization trails in detectors. A neutral particle does not. You only see the neutral kaon when it decays. So Koto watches for the signature of the decay. 2 photons from the pion, with nothing else. The detector's heart is an electromagnetic calorimeter built from undoped cesium iodide crystals. When a photon enters a crystal, it initiates an electromagnetic shower, a cascade of electrons, positrons, and more photons, each generation producing more particles until the energy is fully absorbed. The crystals scintillate, meaning the shower produces flashes of visible light. Photomultiplier tubes at the back of each crystal detect this light, allowing physicists to measure the photon's position and energy. From 2 photons, you can reconstruct the neutral pion, its mass, its direction, its energy, and from the pion's properties, combined with the knowledge that it came from a kaon decay somewhere in the fiducial volume, you can infer the presence of the invisible neutrinos. But here's the nightmare. Background processes can fake the signal. The most dangerous background comes from kaons decaying to 3 pions, where 1 pion is neutral and produces 2 photons, while the other 2 pions escape detection. If those pions are very forward or very low in energy, the veto detectors might miss them. Another dangerous background comes from beam interactions upstream of the detector. Neutrons in the beam can scatter off residual gas or detector material, producing neutral pions that mimic the signal. Koto has invested years in understanding and suppressing these backgrounds. They have upgraded their veto detectors, improved their reconstruction algorithms, and developed sophisticated techniques for estimating background rates from data itself. In 2019, the collaboration reported an intriguing result. 4 events in the signal region where the standard model predicted only 0.1. This caused considerable excitement as it suggested a branching ratio almost 100 times the standard model prediction. But subsequent analysis revealed that the events were likely background from an unappreciated source. Kaon decays occurring upstream of the fiducial volume. The excess vanished once this background was properly accounted for. This is the reality of frontier physics. You are pushing at the edge of what is measurable. Sometimes you think you see something, and it turns out to be an artifact. The only way to be sure is to accumulate more data, improve your understanding, and wait for the truth to emerge. Belle 2 operates in an entirely different regime. The Super Keck Beak Collider produces electron-positron collisions at a center of mass energy of 10.58 billion electron volts. This energy is precisely tuned to the mass of the upsilon 4s resonance, a bound state of a bottom quark and a bottom antiquark. When the upsilon 4s is produced, it decays almost instantly into a pair of B mesons. The 2 B mesons fly apart, traveling only about 200 micrometers before they themselves decay. This is important. The short distance means the decay occurs close to the collision point, where the detector has the best resolution. It also means you can use the silicon vertex detector, a precision tracker made of thin silicon sensors, to separate the decay products of the two B mesons. The Belle 2 detector surrounds the collision point with concentric layers of detection. The innermost is the pixel detector, followed by strips of silicon, then a drift chamber for tracking charged particles. Outside that site, Cherenkov detectors for particle identification, then an electromagnetic calorimeter for measuring photon and electron energies, and finally iron plates instrumented with detectors for muons and neutral hadrons. The strategy for measuring the B meson decay to kaon plus neutrinos relies on tagging. When a B meson pair is produced, you can fully reconstruct one of them, the tag B, from its decay products. This tells you everything about that B meson, its momentum, its energy, its decay vertex. By conservation of momentum and energy, you then know exactly what the other B meson, the signal B, must be. Any deviation from the expected kinematics indicates missing particles, like neutrinos. Belle 2 uses an algorithm called full event interpretation to reconstruct the tag B. The algorithm considers hundreds of possible decay modes using machine learning to assign probabilities. It is computationally intensive but powerful, achieving tagging efficiencies of several %. Once the tag B is reconstructed, you look for a single kaon on the signal side. If the kaon is the only visible particle, and the missing mass and missing energy are consistent with two neutrinos, you have a signal candidate. The measurement is statistics limited. Belle 2 has recorded data corresponding to 424 inverse femtobarns of integrated luminosity. That sounds like a lot, and it corresponds to about 500 million B meson pairs. But the rare decay you are seeking happens only 5 times in a million. You end up with a few dozen signal events, barely enough to claim evidence. The collaboration is working to accumulate much more data. SuperKey KB is being upgraded to deliver higher luminosities, with the goal of reaching 50 inverse attobarns by the early 2030s. That would be more than 100 times the current dataset, enabling precision measurements that could definitively test the standard model. Now let me talk about what it means to measure something at the quantum level. When we say that the standard model predicts the kaon decay branching ratio with 5% uncertainty, what does that mean? It means theorists have calculated the probability of the decay, accounting for all known physics, and the result has an uncertainty of 5%. But where does that uncertainty come from? The calculation involves several steps. First, you need to compute the short distance physics, the weak interaction process where a quark changes flavor and emits a W boson, which then produces a neutrino pair. This part is relatively clean, involving only perturbation theory in the weak and electromagnetic interactions. Second, you need to account for the strong interaction effects. The quarks are not free. They are bound inside mesons by the strong force. This binding modifies the decay amplitude in ways that are difficult to calculate from first principles. For the kaon decays, the strong interaction effects can be parameterized in terms of matrix elements, quantities that describe how the quarks inside the kaon respond to the weak interaction. These matrix elements can be related to experimentally measured quantities, like the rate of other kaon decays, reducing the theoretical uncertainty. Third, you need to incorporate the CKM matrix elements. the fundamental parameters that describe how strongly quarks couple to each other through the W boson. These parameters are not predicted by the standard model. They must be measured. The CKM matrix has 4 independent parameters. Different experiments measure different combinations of these parameters, and there is currently some tension between measurements from different processes. This uncertainty propagates into the rare decay predictions. Burris and his collaborators developed a technique to circumvent the CKM uncertainty. Instead of predicting the rare decay rate directly, they predict ratios of the rare decay rate to other well-measured quantities, like the B meson mixing mass differences or the CP violation parameter in kaon mixing. These ratios depend on the same CKM parameters, so the parameters cancel out in the ratio. What remains is a prediction that depends only on the physics, not on the unknown parameters. This is a clever trick, and it significantly reduces the theoretical uncertainty, but it requires precise measurements of multiple observables, not just the rare decay itself. Let me explain the physics of the GIM mechanism in more detail, because it is central to understanding why these decays are so rare and so powerful. In 1970, when Glashow, Iliopoulos, and Mayani published their famous paper, only 3 quarks were known: up, down, and strange. The charm quark had been proposed by Bjorken and Glashow in 1964, but there was no experimental evidence for it. The problem they were trying to solve concerned strangeness-changing neutral currents. In the weak interaction, quarks can change flavor by emitting a W boson. An up quark can become a down quark. A charm quark can become a strange quark. These are called charge current processes because the W boson carries electric charge, but there is also a neutral carrier of the weak force, the Z boson. Can an up quark emit a Z boson and become a charm quark? Can a strange quark become a down quark? If the answer were yes, there would be flavor-changing neutral currents at tree level, the simplest diagrams, without any loops. And these processes would be large, comparable in strength to the ordinary charged currents. But experiments showed that flavor-changing neutral currents were highly suppressed. The decay of a long-lived neutral kaon to 2 muons, for instance, occurred far less often than naive estimates predicted. Something was preventing the neutral currents from changing flavor. Glashow, Iliopoulos, and Mayani showed that the suppression arose naturally if there were 4 quarks instead of 3. With the addition of the charm quark, the charged weak current could be written in a way that made the neutral current diagonal in flavor, meaning it could not change quark flavors at tree level. But that was not the end of the story. Even with no tree-level flavor-changing neutral currents, such currents could arise at 1 loop level. A strange quark could emit a W boson and become an up quark, which then absorbs a W boson and becomes a down quark. The net effect is a strange quark becoming a down quark, mediated by 2 W bosons in a box diagram. This loop process is not forbidden, but it is suppressed. The key insight of GIM was that the suppression comes from interference. If you sum over all possible intermediate quarks in the loop, up, charm, and eventually top, the amplitudes partially cancel. For perfect cancellation, the quarks would need to have the same mass, but they do not. The top quark is vastly heavier than the up and charm quarks. The imperfect cancellation leaves a residual amplitude proportional to the quark mass differences. And because the top quark is so heavy, its contribution dominates. This is why the rare decays are sensitive to physics at high energy scales. The amplitude depends on the masses of the virtual particles in the loop. If new heavy particles exist, they would contribute to the loop just like the top quark, modifying the amplitude. The charm quark was discovered 4 years after Jim's paper in 1974. The discovery came from 2 independent experiments, one at Brookhaven National Laboratory, led by Samuel Ting, and one at the Stanford Linear Accelerator Center, led by Burton Richter. Both groups observed a narrow resonance, a sharp peak in the rate of particle production, at a mass of about 3.1 billion electron volts. The peak was so narrow that it could only be explained by a bound state of 2 heavy quarks, decaying through the electromagnetic interaction rather than the strong interaction. The new particle was called J by Ting's group and Psi I by Richter's group. Today, it is known as the J-Psi meson. The JPSI is made of a charm quark and a charm antiquark. Its discovery was hailed as the November Revolution in particle physics, and Ting and Richter shared the Nobel Prize in 1976. The confirmation of the charm quark was a stunning vindication of the Jim mechanism, a theoretical prediction made to solve a puzzle in rare decays, had led to the discovery of a new fundamental particle. This is the precedent that gives hope to today's rare decay hunters. The Magnificent Seven could be pointing to new particles, just as the suppression of neutral currents pointed to the charm quark half a century ago. Let me describe what theorists think might be out there. The possibilities are constrained by the existing data. Whatever new physics exists, it must be consistent with the fact that the standard model works extremely well at energies below a few tera-electron volts. New particles must be either heavy, weakly coupled, or both. One popular framework is supersymmetry. In supersymmetry, every known particle has a partner particle with different spin. Quarks have squark partners. Leptons have slepton partners. The W and Z bosons have wino and xeno partners. These partners have never been observed, so they must be heavier than the energies we have probed. Supersymmetric particles would contribute to the rare decays through loop diagrams. Squarks and gauginos could appear as virtual particles, modifying the decay rates. The predictions depend on the masses and couplings of the supersymmetric particles, which are not determined by the theory itself. Different parameter choices give different predictions, some enhancing the decay rates and some suppressing them. If supersymmetry is realized in nature at energy scales of tens of tera-electron volts, the rare decays would be sensitive to it. The pattern of deviations from standard model predictions could reveal the structure of the supersymmetric spectrum. Another possibility is extra dimensions. In some theories, space has more than 3 dimensions, but the extra dimensions are curled up so small that we do not notice them. Particles propagating in the extra dimensions would appear from our perspective as towers of increasingly massive states. These Kaluza-Klein excitations, named after the physicists who first proposed extra dimensions in the 1920s, would contribute to loop processes, potentially affecting the rare decays. A third possibility is a composite Higgs sector. In the standard model, the Higgs boson is an elementary particle, but some theories suggest It might actually be a bound state of more fundamental constituents, analogous to how a proton is made of quarks. If the Higgs is composite, there would be additional particles associated with its substructure. These particles would be heavy, perhaps in the tens of tera-electron volts range, and would affect the rare decays. Each of these scenarios, supersymmetry, extra dimensions, composite Higgs, has different predictions for which rare decays would be enhanced and which would be suppressed. The Magnificent Seven provide a comprehensive test capable of distinguishing between the possibilities. The Future Circular Collider represents the long-term vision for high-energy physics. CERN's feasibility study, completed in March 2025, envisions a 90.7-kilometer tunnel beneath the Franco-Swiss border, roughly 3.5 times the circumference of the Large Hadron Collider. The project would proceed in 2 stages. The first stage, called FCCE, would be an electron-positron collider operating at energies ranging from 90 to 365 billion electron volts. It would serve as a factory for producing Higgs bosons, W and Z bosons, and top quarks in enormous quantities. The precision of electron-positron collisions is unmatched. Unlike proton collisions, where the constituent quarks and gluons carry variable fractions of the proton's momentum, electron-positron collisions have a precisely known initial state. This allows measurements of fundamental parameters with unprecedented accuracy. FCCE would run for about 15 years, producing roughly 3 million Higgs bosons, 240 million W boson pairs, and over 6 trillion Z bosons. The second stage, called FCCHH, would replace the electron-positron collider with a proton-proton collider, similar to the Large Hadron Collider, but at vastly higher energy. Using advanced superconducting magnets with fields of 16 Tesla, more than twice the strength of LHC magnets, FCCHH would achieve collision energies of approximately 100 tera-electron volts. That is more than 7 times the energy of the LHC. At 100 tera-electron volts, physicists could directly produce particles far heavier than anything the LHC can access. The mass reach for new particles would extend to tens of tera-electron volts, covering much of the territory that the rare decays are indirectly probing today. If the rare decays reveal deviations from the standard model, FCCHH might be able to produce the particles responsible. The loop effects observed in the decays would become tree-level effects in the collider, direct production and study of the new physics. But FCCHH would not begin operations until the 2070s or beyond. A final decision on whether to build the FCC is expected around 2028. If approved, construction could start in the early 2030s. This is why the rare decays are so important. They provide a window into the physics of the Future Circular Collider, decades before the collider itself exists. There is a beautiful complementarity between direct and indirect searches. Direct searches producing new particles in high-energy collisions tell you what the particles are, their mass, their spin, their couplings to other particles. You can study them in detail, measure their properties, understand their role in nature. But direct searches have a limitation. You can only produce particles that are lighter than the energy of your collision. Beyond that threshold, you are blind. Indirect searches, looking for effects of new particles in precision measurements, can reach beyond the energy threshold. The new particles appear only as virtual states, but their effects are measurable. However, indirect searches have their own limitation. They tell you that something is there, but they do not tell you exactly what. The deviations from standard model predictions could be explained by various new physics scenarios. Without additional information, you cannot uniquely determine the culprit. The ideal strategy combines both approaches. Use indirect searches to discover the presence of new physics and constrain its properties. Then build a collider powerful enough to produce the new particles directly and complete the picture. The rare decays are the scouting party. The future circular collider is the main force. I want to emphasize how extraordinary it is that we can predict these rare decay rates at all. The standard model is not just a description of particles. It is a predictive framework that allows calculations of arbitrary precision. When theorists compute the branching ratio for kaon decay to pion plus neutrinos, they are performing a calculation that involves integrating over all possible configurations of virtual particles, summing up contributions from millions of Feynman diagrams, accounting for quantum chromodynamics, corrections that shift the result by factors of 2 or more. The calculation has been refined over decades. Leading order contributions were understood in the 1980s. Next to leading order corrections were computed in the 1990s. Next to leading order corrections, electroweak corrections, long-distance contributions from light intermediate states, all have been added over the years. The result is a prediction with theoretical uncertainty at the few percent level. That is remarkable, given the complexity of the physics involved. And it is this precision that makes the experiments meaningful. If the theoretical uncertainty were 30%, a 50% deviation would not be significant. But with theoretical uncertainty at 5%, a 50% deviation stands out. The interplay between theoretical and experimental precision is crucial. Neither can make progress alone. Theorists need experimental measurements to test their calculations. Experimentalists need theoretical predictions to know what to look for. This is the essence of the scientific method, played out at the frontier of human knowledge. As I conclude, I want to return to the detective analogy I started with. We are hunting for something we cannot see. We know it exists. The evidence is overwhelming, but we cannot find it directly. So we look for traces, fingerprints, echoes. The rare decays are those traces. Each decay is a window into a world we cannot otherwise access. Each measurement pushes the boundary of what we know. The journey is long, the progress is slow. There are false alarms and dead ends. But the destination is one of the most profound questions humanity has ever asked. What is the universe made of? The standard model tells us about quarks and leptons, about W and Z bosons, about the Higgs field that gives mass to everything. But it does not tell us about dark matter, which outweighs ordinary matter by a factor of 5. It does not tell us why there is more matter than antimatter. It does not explain the vast hierarchy between the strength of gravity and the other forces. These are not abstract questions. They concern the very fabric of existence. Why is the universe the way it is? Why can it support stars and planets and life? Somewhere in the answers to these questions lies a physics beyond what we know, and somewhere in the rare decays of kaons and B mesons that physics might be leaving its signature. 7 decays, each measured with painstaking care, each compared to predictions computed with decades of effort. The hunt continues. In laboratories around the world, detectors are watching, recording, analyzing. Billions of kaons are produced every year. Millions of B mesons, each one a lottery ticket. A chance that this particular decay will be the rare one, the one that happens fewer than once in 10 billion tries. The physicists running these experiments are patient. They have to be. This is not the physics of instant gratification. This is the physics of the long game, the slow accumulation of evidence, the gradual reduction of uncertainty. But the stakes could not be higher. If new physics is found in these decays, it will reshape our understanding of the universe at its most fundamental level. It will open doors that have been closed for a generation. It will point the way toward answers to questions we have been asking since the beginning of science. What is matter made of? Why is there something rather than nothing? What are the ultimate laws that govern reality? And if the decays all agree with the standard model, even that would be profound. It would tell us that the new physics is hiding in places we have not thought to look, that our assumptions need to be revisited, that the universe is even stranger than we imagined. Either way, we learn. That is the beauty of science. Every result, whether expected or surprising, teaches us something. The universe speaks through data, and we are learning to listen. 7 decays, fewer than once in 10 billion. The fingerprints of the Zeptouniverse. The search goes on. There is a story I want to tell you about the nature of scientific discovery. In 1964, 2 physicists at Brookhaven National Laboratory, named James Cronin and Val Fitch, were studying the decays of neutral kaons. They expected to confirm what everyone believed, that the laws of physics looked the same when you simultaneously reversed all charges and flipped the universe in a mirror. This symmetry is called CP symmetry. C for charge conjugation, P for parity. CP symmetry seemed fundamental. If you took any physical process, replaced all particles with their antiparticles, and reflected everything in a mirror, the resulting process should behave identically to the original. This was not just a theoretical prejudice. It was supported by extensive experimental evidence. Cronin and Fitch set out to confirm this. Their experiment used a beam of neutral kaons produced at the Brookhaven accelerator. Neutral kaons are peculiar particles. They exist in superpositions of matter and antimatter, oscillating between particle and antiparticle states as they travel. There are 2 types of neutral kaon. The K-short, which lives for about 1/10 of a nanosecond and decays primarily to 2 pions, and the K-long, which lives about 500 times longer and decays to 3 pions. The difference in lifetimes arises from CP symmetry. 2 pions have CP equals +1, while 3 pions have CP equals -1. If CP is conserved, a particle with CP equals -1 cannot decay to 2 pions. The K-long has CP equals -1. Therefore, if CP is exactly conserved, the K-long should never decay to 2 pions. Any 2-pion events observed far from the kaon source, far enough that all the K-shorts have decayed, must be experimental errors. Cronin and Fitch built their apparatus. They let the kaon beam travel far enough that only K-longs remained. Then they looked for 2-pion decays. They found them. About 2 in every 1,000 K-long decays produced 2 pions instead of 3. CP symmetry was violated. The result was stunning. It implied that the laws of physics distinguish, ever so slightly, between matter and antimatter. The universe, at its most fundamental level, is not perfectly symmetric. Cronin and Fitch won the Nobel Prize in 1980, but the deeper significance of their discovery took decades to appreciate. We now understand that CP violation is one of the ingredients needed to explain the matter-antimatter asymmetry of the universe. According to the Big Bang theory, the early universe should have contained equal amounts of matter and antimatter, which should have annihilated each other completely, leaving nothing but radiation. Yet here we are, made of matter, in a universe filled with matter. Something must have tipped the balance. Something must have caused a tiny excess of matter over antimatter, so that when the annihilation was complete, a residue of matter remained. CP violation is one of the necessary ingredients. Without it, the laws of physics would treat matter and antimatter identically, and no asymmetry could develop. The kaon system was the first place where CP violation was observed, but the amount of CP violation in kaons is far too small to explain the observed matter excess. There must be additional sources of CP violation beyond what the standard model predicts. This is one of the deepest motivations for searching for new physics in rare kaon decays. The neutral kaon decay to pion plus neutrinos, one of the Magnificent Seven, is a direct probe of CP violation. If the decay rate differs from the standard model prediction, it could indicate new sources of CP violation, potentially enough to explain our existence. Let me tell you about the precision frontier, because it is where much of modern physics is heading. For most of the 20th century, particle physics advanced by reaching higher and higher energies. Each new generation of accelerators produced particles that had never been seen before. The proton, the neutron, the positron, the muon, the pion, the strange particles, the charmed particles, the bottom quark, the top quark, the W and Z bosons, the Higgs boson, all discovered by smashing particles together with ever greater violence. But there is another way to discover new physics, by measuring known processes with ever greater precision. Consider the magnetic moment of the electron, a measure of how strongly the electron spin couples to magnetic fields. In the standard model, this quantity can be calculated to extraordinary accuracy using quantum electrodynamics. The prediction reaches 12 significant figures of precision. And the measurement? Experiments at Harvard and elsewhere have measured the electron's magnetic moment with comparable precision. The agreement between theory and experiment is stunning. One of the most precise tests of any scientific theory in history. But here is the key. If there were new particles that coupled to the electron, they would slightly shift the magnetic moment. The shift would be tiny, perhaps in the 11th or 12th decimal place, but with sufficient precision, it could be detected. This is the essence of the precision frontier. You do not need to produce new particles directly. You need to measure known quantities so accurately that any deviation from prediction is visible. The rare kaon and B meson decays operate on the same principle. You measure a branching ratio with percent-level precision. You compare it to a prediction with percent-level uncertainty, and if they disagree, something new is present. The precision frontier is complementary to the energy frontier. One reaches for heavy particles by producing them directly. The other reaches for heavy particles by detecting their subtle influences on lighter particles. There is a concept in physics called naturalness, and it haunts the field. The Higgs boson has a mass of about 125 billion electron volts. This might seem like just a number, but it is profoundly puzzling. In quantum field theory, the mass of a particle receives corrections from virtual particles, the same loop diagrams we discussed for rare decays. These corrections depend on the masses of the particles in the loops. For the Higgs boson, the loop corrections from the top quark alone push the Higgs mass up to enormously high values, toward the Planck scale, where gravity becomes quantum mechanical at energies of 10 to the 19th billion electron volts. To get a Higgs mass of only 125 billion electron volts, there must be incredible cancellations between different contributions. The bare Higgs mass and the loop corrections must nearly perfectly cancel, leaving only a tiny residue. This fine-tuning is unnatural. It suggests that we are missing something. Supersymmetry was invented partly to solve this naturalness problem. In supersymmetry, every particle has a partner with opposite spin statistics. The loop corrections from particles and their partners cancel exactly, eliminating the enormous contributions that make the Higgs mass unnatural. But for this cancellation to work, the supersymmetric partners must have masses not too different from the ordinary particles. If the superpartners are too heavy, the cancellation becomes imperfect and the naturalness problem returns. The fact that the Large Hadron Collider has not found supersymmetric particles means that if they exist, they must be heavy, heavier than a few tera-electron volts. This does not rule out supersymmetry, but it means that supersymmetry does not solve the naturalness problem as elegantly as theorists hoped. The rare decays offer an alternative probe. Even if supersymmetric particles are too heavy to produce at the LHC, they could still appear as virtual particles in loop diagrams, affecting the rare decay rates. If deviations from standard model predictions are observed in the Magnificent Seven, it could point toward supersymmetry or toward other solutions to the naturalness problem, like composite Higgs models or extra dimensions. Let me explain why neutrinos are so important in the rare decays we have been discussing. Neutrinos are the ghosts of the particle world. They have no electric charge, so they do not interact electromagnetically. They have only the faintest interaction with matter through the weak force. A neutrino can pass through a light year of lead without interacting. This makes them invisible to detectors. When a kaon decays to a pion and two neutrinos, you see the pion and nothing else. The neutrinos carry away energy and momentum, leaving a signature of missing mass. But this invisibility is also a virtue. Because neutrinos are so hard to detect, they are also clean probes of fundamental physics. Backgrounds involving neutrinos are minimal because most other processes produce visible particles. The rare decays to neutrino pairs are theoretically cleaner than decays to charged leptons because there are fewer complicating factors from electromagnetic interactions. Moreover, neutrinos themselves are mysterious. The standard model originally assumed neutrinos were massless, but experiments over the past 3 decades have shown that neutrinos have mass, tiny mass, perhaps 1 million times smaller than the electron, but mass nonetheless. This discovery won the Nobel Prize in 2015 for Takaaki Kajita, and Arthur MacDonald. It also created a puzzle. In the Standard Model, neutrinos get their mass in the same way other particles do, through coupling to the Higgs field. But for this to work, there must be right-handed neutrinos, partners to the left-handed neutrinos we observe. We have never seen a right-handed neutrino. If they exist, they must be either very heavy or very weakly interacting. Some theorists propose that right-handed neutrinos are extremely heavy, perhaps at the scale of grand unification, 10 to the 16th billion electron volts. If so, these heavy right-handed neutrinos could influence the rare decays. They would appear in loop diagrams, modifying the amplitudes in ways that depend on their masses and couplings. The rare decays to neutrino pairs are therefore not just probes of the weak interaction. They are probes of the entire neutrino sector, including particles we have never observed. I have been talking about 7 decays, but I should mention that the Magnificent Seven are part of a broader landscape. There are dozens of rare decays that physicists are studying, each with its own sensitivities and challenges. The 6 I mentioned earlier are the theoretically cleanest, but others provide important complementary information. For instance, the decay of a B meson to a kaon star plus a muon-antimuon pair, where kaon star is an excited state of the kaon, has shown interesting hints of anomalies over the past decade. The distribution of the decay products in angle and momentum seem to disagree with Standard Model predictions at the level of several standard deviations. These anomalies generated tremendous excitement. They suggested violations of lepton flavor universality, the principle that electrons, muons, and taus interact identically, except for their masses. But subsequent analyses, with more data and better understanding of backgrounds, have diminished the significance of the anomalies. The LHCb experiment recently reported that, with their full dataset, the ratios of electron and muon decay rates agree with Standard Model predictions. This is the nature of frontier physics. Anomalies appear, generate excitement, and then either strengthen into discoveries or fade away with more data. The Magnificent Seven have been chosen precisely because they are less susceptible to these fluctuations. Their theoretical predictions are cleaner, and the experiments are designed specifically to measure them. Let me describe what would happen if a definitive deviation were found. Suppose Na62 accumulates enough data to measure the charge kaon branching ratio with 10% precision. Suppose the result is 15 in 10 billion, clearly higher than the Standard Model prediction of about 8 in 10 billion. The first reaction would be skepticism. Physicists would scrutinize every aspect of the analysis, looking for systematic errors, misunderstood backgrounds, anything that could explain the discrepancy without invoking new physics. Other experiments would attempt to confirm or refute the result. Koto might push to higher sensitivity on the neutral kaon decay, looking for a correlated deviation. Belle too would examine the B meson decays with renewed urgency. LHCb would squeeze every last bit of precision from the muon pair modes. Theorists would go into overdrive, proposing models that could explain the pattern of deviations. Papers would flood the preprint servers. Conferences would buzz with speculation. Careers would pivot toward the new anomaly. If the deviation held up, if multiple independent experiments all pointed in the same direction, if no systematic explanation emerged, if the statistical significance grew to 5 sigma and beyond, the physics community would declare a discovery. And then, the real work would begin. What is the new physics? Is it a Z-prime boson, a leptoquark, a supersymmetric particle, a consequence of extra dimensions, something entirely unexpected? The pattern of deviations across the Magnificent Seven would constrain the possibilities. Correlations between different decay modes would point toward specific models. The mass scale of the new physics could be inferred from the size of the deviations, and physicists would immediately start planning the next generation of experiments. Can we produce the new particle directly? How powerful a collider would we need? What other effects should we look for? This is how physics progresses. Not in sudden revolutions, though those happen occasionally, but through the gradual accumulation of evidence, the careful elimination of alternatives, the construction of ever more comprehensive theories. There is a philosophical question underlying all of this. Why should the universe be comprehensible? The fact that we can write down equations that describe particles and forces, that we can calculate branching ratios to the part per billion level, that our predictions agree with measurements made in detectors built from the same atoms those equations describe. This is not obvious. It could have been otherwise. Eugene Wigner, one of the founders of quantum mechanics, wrote a famous essay called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He marveled at how mathematical structures invented by pure mathematicians with no regard for physics turned out to be exactly the tools needed to describe the physical world. Group theory, invented to classify symmetries of algebraic equations, became the language of particle physics. Riemannian geometry, invented to study curved surfaces, became the foundation of general relativity. Complex analysis, probability theory, topology, all found unexpected applications in physics. Why? We do not know. Perhaps the universe is inherently mathematical, and mathematics is not invented but discovered. Perhaps our brains, evolved to survive in a particular environment, happen to be configured to perceive the patterns that govern that environment. Perhaps we are missing something profound about the relationship between mind and matter. The rare decays are a small corner of this vast mystery, but they embody the spirit of scientific inquiry, the conviction that the universe has an order, that we can discover it through careful observation and rigorous reasoning, and that the truth, once found, will be more beautiful than our imaginations could devise. I want to end with a meditation on time. The CERN was discovered in 1947. The GIM mechanism was proposed in 1970. The charm quark was found in 1974. CP violation was confirmed that same year in Cairns. Now it is 2026. 80 years since Rochester and Butler saw their V particles, half a century since Glashow, Iliopoulos, and Maiani predicted the charm quark. Decades of experiments, billions of dollars invested, thousands of physicists' careers. And we are still studying kaons, still extracting secrets from these strange particles, still hoping that they will reveal something beyond what we know. This is the timescale of fundamental physics. Progress is measured in decades, not months. The questions we ask take generations to answer. The Magnificent Seven represent decades of theoretical refinement and experimental preparation. The NA62 experiment was first proposed in the early 2000s. Belle 2 builds on the legacy of Belle, which ran for a decade before it. Koto continues a tradition of calm physics at J-Park that stretches back decades more. The answers we seek may come in the next 5 years, or they may come in 20, or the standard model may continue to hold, forcing us to look elsewhere, to rethink our assumptions, to start again with new ideas. Either way, the search continues. The kaons keep decaying. The detectors keep watching. The data keeps accumulating. Somewhere in that data, in the rare events that happen fewer than once in 10 billion times, the universe is telling us something. We just have to learn how to listen. Let me give you a final perspective on scale. The Large Hadron Collider probe's distances down to about 50 zeptometers. That is 50 times 10 to the minus 21 meters. To understand how small that is, consider this sequence. A meter is roughly the height of a small child. A millimeter is the thickness of a credit card. A micrometer is the size of a bacterium. A nanometer is the width of a few atoms. A femtometer is the size of a proton. A zeptometer is 1,000,000 times smaller than a femtometer. It is to a proton what a proton is to a small town. This is where we are exploring. This is the frontier of human knowledge about the structure of matter. And yet, the rare decays can reach even further. The Zeptouniverse that Andrei Buras describes extends to 10 to the minus 21 meters, corresponding to energies of 200 tera-electron volts. This is 4 times smaller and 4 times more energetic than the LHC can directly probe. The Magnificent Seven are our telescopes into that realm. Not optical telescopes that collect light, but precision instruments that collect statistics, counting rare events, measuring tiny deviations, inferring the presence of what cannot be seen. Consider what we have learned from kaons and B-mesons already. The Kaon system gave us strangeness, the first hint that quarks come in flavors beyond up and down. It gave us CP violation, the first evidence that nature distinguishes between matter and antimatter. It gave us the Jim mechanism and the prediction of the charm quark, vindicated 4 years later by experiment. The B-meson system gave us precise measurements of the CKM matrix, allowing tests of the standard model at the few percent level. It gave us observations of B-meson mixing, confirming the theory of neutral meson oscillations. It gave us direct CP violation in the B system, consistent with the standard model, but constraining alternative theories. Each of these discoveries came from studying particles that existed for only a billionth of a second before decaying. Each required patience, precision, and faith that the universe's secrets would reveal themselves to those who looked carefully enough. The Magnificent Seven continue this tradition. They are not merely measurements, they are probes of the deepest structure of reality. I've talked a lot about what might be found. Let me also acknowledge what might not be found. It is possible that the standard model is exactly correct up to energy scales far beyond what the rare decays can probe. It is possible that new physics exists only at the Planck scale, or in sectors that do not couple to quarks and leptons, or in ways we have not imagined. If the Magnificent Seven all agree with standard model predictions, if the deviations we are currently seeing fade away with more data, it will not be a failure. It will be knowledge. We will know that physics is unchanged up to 200 tera-electron volts, at least in certain sectors. We will know that whatever explains dark matter and the matter-antimatter asymmetry and the other puzzles, it does not manifest strongly in rare meson decays. This is valuable information. It guides theory. It focuses future experiments. It tells us where not to look, which is just as important as telling us where to look. Science progresses not only through discoveries, but through exclusions. Every null result narrows the space of possibilities. Every successful standard model prediction is a constraint on what new physics can exist. The Magnificent Seven will teach us something either way. The experiments continue. NA62 is preparing for its next data-taking run. The collaboration is analyzing data already collected, refining their techniques, reducing uncertainties. COTO is upgrading its detectors, pushing toward the sensitivity needed to see the standard model neutral kaon decay. Belle 2 is accumulating luminosity at super KEKBB, building the dataset that will enable percent-level measurements of the B meson neutrino modes. LHCb is upgrading for Run 3 of the Large Hadron Collider, with improved tracking and triggering that will enhance its sensitivity to rare B decays. Around the world, theorists are refining their predictions, reducing uncertainties, developing new strategies for extracting information from data. This is the global enterprise of particle physics. Hundreds of institutions, thousands of scientists, decades of collective effort, all focused on understanding the fundamental nature of reality. There is something hopeful about this endeavor. In an age of division and discord, particle physics remains one of humanity's great collaborative achievements. Scientists from dozens of countries, speaking different languages, holding different beliefs, working together toward a common goal. The experiments at CERN involve physicists from Europe, Asia, the Americas, Africa, Australia. They compete fiercely for resources and credit, but they also share data, techniques, and insights freely. This is how science works at its best. Not as a zero-sum game, but as a collective exploration. Every measurement advances our understanding. Every null result constrains the possibilities. Every success is a success for all. The Magnificent Seven are not just measurements. They are embodiments of human curiosity, human ingenuity, human cooperation. They represent our best efforts to understand the universe we inhabit. Let me leave you with this thought. Somewhere in the world right now, a kaon is decaying. It might decay into a pion and a muon and a neutrino, the common mode, nothing special. But 1 in 10 billion times, it decays differently. It produces a pion and 2 neutrinos, no muon, just missing energy, a ghostly signature that lasts for a fraction of a nanosecond before vanishing. And when it does, for that briefest of moments, the laws of physics that govern our existence, the forces and particles that make up everything we see, are tested. The standard model makes a prediction. Nature renders a verdict. If the verdicts keep agreeing with the predictions, we learn that the standard model holds. If they disagree, we learn that something else is out there. Either way, we move forward. That kaon, decaying in a detector in Geneva or Tsukuba, is contributing to human knowledge. Its decay is a single data point in a statistical ensemble, a single trial in a cosmic experiment, billions of kaons, millions of B mesons, trillions of collisions, and from all that chaos, clarity emerges. Patterns reveal themselves. The universe yields its secrets. This is the power of physics. This is the beauty of the Magnificent Seven. 7 decays. 7 windows into physics beyond our understanding. 7 fingerprints left by particles we cannot see, forces we cannot directly feel, structures we can barely imagine. The Magnificent Seven, CERN's secret weapon in the hunt for what lies beyond. The search goes on.